Okay. So yeah, hello everyone. This is our first talk of 2025. Today we have Kaustav Kashyap Das, who is currently he is the student at California Institute of Technology. So Kaustav, as far as I know, completed his undergraduate degree from IIT Kanpur and then moved to Caltech to hang out with Sheldon Leonard, Raj, and Howard. Anyway, joking aside, today he'll be delivering a talk titled Cosmic Fireworks, the Explosive Collapse of Stars. So students, you can interact with him in English or Assamese or Hindi, any language that you may like, with any kind of queries related to the talk or maybe research or maybe your career. And if you're not comfortable speaking over the mic, you can type your questions in the chat box as well. So yeah, over to you, Costa.
Okay, yeah, thank you for the kind introduction. Good morning, everyone. Thanks for joining on a Sunday morning right after a India-Australia test match. Um, my plan is to give a talk of around 50 minutes, 50 minutes. I'll include discussions on the some of the basic introduction of the science that I'm doing now. I'll also talk about some career stuff at the end, but feel free to stop me in the middle of the talk if you have any questions. I have not used Google Meet before, so I don't know if the raise hand or something works here. But if you have any questions, feel free to interrupt me during the talk at any time. Okay, so let's get started. So I'll first start out with the very basics of what is a supernova explosion. So I saw that in the list of talks that were there in this, as part of this, there were already a lot of astronomy talks. So I guess many of you, if you have attended a lot of this a bit more regularly, then you're probably familiar with some of this. But I'll still go over some of the very basic stuff for those who are not very familiar. So, as probably all of you know, a star is kind of like a big ball of plasma. So, what powers a star or what gives a star its light is that there is nuclear fusion that's going on in its core, which is burning, for example, hydrogen to helium, in most cases, for example, like our sun, or into further elements as you go on. So there's this pressure from the core that's pushing against the star, but that's being balanced by the gravity of the star itself because of the massive because of its mass. Um, so we probably all of you are familiar with this diagram. This I think this came come up in class 11 physics book or class 12 physics book, where you show the nuclear stability of different elements. And so what happens is that initially you are fusing hydrogen to helium, but then once you run out of that hydrogen, what happens is now you're left with helium at the core. So now, now that you are no longer fusing something, what happens is gravity kind of wins over the outward pressure that's being given out, and then the temperature and the pressure at the core becomes even more high. Then what happens is that now the helium starts getting fused to carbon, the carbon gets fused to oxygen, and so on. However, this process cannot go on beyond iron. The reason for is that after iron, to further form heavier elements, you need to provide energy instead of it being an exothermic process. I guess these are some of the jargons most of you are already familiar with, right? So as I mentioned, so the inner structure of of a star at the end of its iron fusion cycles would look something like this. So you are progressively forming heavier and heavier elements at the core of the star, starting from hydrogen to helium to carbon, oxygen, neon, magnesium, till iron. But once you form iron, you can no longer fuse anything else. So now this balance between gravity and nuclear fusion results in a break of the balance. So the nuclear fusion loses out and then gravity wins. And so what happens is that the entire outer material of the star basically collapses onto itself, resulting in this very magnificent explosion called a supernova explosion. So this is a animated version of supernova explosion of the Crab Nebula. The actual supernova of this particular thing went off in 1054 AD, roughly 1100 years ago, and this is what the remains of it looks like currently. So just to summarize, a supernova is the explosive end or the explosive explosion of a massive star as it fuses up to iron. So there are different kinds of all the supernova flavors. I'll be just focusing on core collapse supernova, which I described in my previous slides. So astronomers have been naming them, categorizing them into different categories depending on what elements are present. So, for example, as I mentioned in this diagram, at the outer envelope you have hydrogen, then you have helium. If during the supernova explosion you still see hydrogen, it's called a type 2 supernova. If you get rid of the hydrogen and you just see helium, then it's something called a 1b supernova. If you do not see either hydrogen or helium, then you call them something called a type 1c supernovae. But the question that arises is that how do we know what elements are present in the supernovae? So it's fine that we discovered a supernova, but then how do we know what elements and all are present? So the fundamental idea of this is very simple to some of the basic physics that we already know. For example, the idea is that we put a fancier version of a prism called a spectrograph, and then basically disperse the light that we have from the supernova explosion. And the light that we get from this explosion, then we can break it up into the strength of those lines at different wavelengths. And based on those wavelength abundances, we can actually predict which elements are present. And the reason for that is simple. Just like every human has a very unique fingerprint, each element also has a very unique absorption or emission spectrum. Again, something which you probably read in class 11, 12. So the next part of the doc is then why should we care about these supernova explosions? Why should we study them, or why are they interesting? So for me, one of the most interesting thing about supernova explosions is that I mentioned that the stars formed all of these elements in its belly, starting from helium to iron, and we need some process to disperse these elements that were synthesized in the core of the star back into the universe. And a supernova explosion does exactly that process. So in a way, a lot of the elements that we see in our everyday life, for example, the calcium in our bones, the oxygen that we breathe every day, the iron in our blood, all of them, all of them that are present in our bodies have actually come because of the supernova explosions, which disperses these elements out from the core of the star out into the universe. Another very important reason for studying supernovae explosions is that they are an amazing lab for probing various kinds of different astrophysics. For example, the temperatures going up to few million kelvins, the pressure and the high amount of energy, all of this cannot be produced in like man-made labs. So all these supernovae explosions provide a very natural laboratory for us to further probe some very interesting high energy phenomena that are going on. Some of the other reasons are that once you undergo a supernova explosion, what you are left out, what remains behind is a compact object called a black hole or a neutron star. I think others have spoken about these topics in their talks. So it's important to understand their abundances. To understand their abundances properties, it's also important to understand what a supernova is. Then, as I mentioned, it's important to understand what the metal enrichment of our galaxies, of our neighborhood, of the solar system, of our Earth is, and how it relates back to the supernova explosions. I saw that the last talk on the series was about gravitational waves. So it's this supernovae that forms these neutron stars or these black holes, which eventually merge together to give these gravitational waves that LIGO detects. It's also possible that a supernova alone, the explosion of a supernova alone, can produce gravitational waves, but that's yet to be detected. These are also sources of something called very high energy particles called cosmic rays. Understanding supernova is important because they are basically the death of stars, right? So they contribute a lot towards understanding of the stellar evolution process, what goes on in the core of the nuclear fusions of the star, how it contributes back to the overall evolution of the galaxy. And last but not the least is the cosmology. So cosmology is basically trying to understand the entire state of the universe. When did it begin? How fast is it expanding? A particular type of supernova called type 1a supernova was used to actually determine the fact that our universe is accelerating. And the Nobel Prize in 2011 was given to this. So as you can see, supernova explosions provide a amazing laboratory to study any kind of a variety of different physics and astrophysics. Hopefully, I've motivated you enough that it's important and interesting to study supernovae explosions. The next part of the talk, I'll focus on how do we actually discover them. Um, so a supernova, when it explodes, the energy that it emits, for example, our sun has been burning for 5 billion years. It will continue to burn for 5 billion years. And the amount of energy that's released during a few seconds of the supernova explosion is almost equal to the energy that would be produced by a massive star in its entire span of few millions or few hundreds of millions of years. So you can imagine that a supernova is a very, very high energy process. So when it explodes, it can outshine an entire galaxy. So if you know, a galaxy has roughly 100 billion stars, and when a supernova happens, just because from one star, it can outshine the light of 100 billion stars. So if that supernova would have happened very close by, it's actually detectable with the naked eye. And historically, there are lots of records of this. So the first cave painting that I show is actually from India, from Kashmir. I think this was many thousands of years ago. So where they drew two suns in the sky. So for example, if a star close by in the Milky Way were to undergo a supernova explosion, we would actually see two suns in the sky for a few weeks. This actually was recorded for the supernova in 1054 AD. So the yellow text in Chinese that's here actually says that they saw a new guest star. So when they saw this new object on the sky, by the time they knew that it was not a planet, it was not a moving satellite, not the moon. So they termed it nova, or which is a name for a new star or a guest star. So now we know that it's not actually a new star, but rather the explosive end of a old star. Right. So there's a historical timeline of how people have tried to study this, how people have tried to understand this magical phenomena. I think, yeah, if you can imagine 1,000 years ago, you see a new object all of a sudden in the sky, you'd be pretty fascinated by it. So the very basic principle to discover this is very simple. It's just finding the difference, a game that we have always been playing in newspapers or magazines. So for example, on the left, I have an image of the Large Magellanic Cloud. And on the right, I have the same image, but taken few days after the first image. So you can clearly see that previously there was a massive star here, but after a few days, you see that there's now a very bright object there. So just from this. So what you would do is that you'll take the second image, and then you'll subtract the first image out from it. And what would remain is just a bright blob at the center. And this is a very simplistic concept behind the discovery of this objects called supernova, or any kind of astronomical transients which appear in the night sky for a few weeks or days and then disappear after a while. So historically, this was first done by Fritz Zwicky, who's also famous for discovering dark matter. So he did it on. He was part of Caltech when he discovered he made a catalog of tens of um, supernovae from around 1920s to 1940s. So he used telescopes on Mount Wilson Observatory and Palomar Observatory, both very close to Caltech. So the way they did it actually was that they would note everything down on a photographic plate. For example, this is a photographic plate from 1964. These are actual pictures from. These are still there if you ever go to Palomar Observatory. There's a museum where they keep these photographic plates. You can see that in 1964, this is what this part of the sky looked like. And in 1971, this is what the same part of the sky looked like. And they saw that there's a new blob in that sky, which was not present in the images taken in 1964. So actually, they would stare under like lenses, the kind of sort of a microscope or magnifying lens, and then they would stare at every point to look for new dots that appear in the sky. And using this technique, they actually discovered more than 50 supernovae over a span of 20 years. Now, of course, we do not use this analog method. What we do is, thanks to the era of digital CCD cameras, we are now actually discovering thousands of supernovae every year compared to the dozens of supernovae discovered over a decade. So this era, this era is now the era of wide field sky surveys, thanks to a lot of advancement and development in the field of instrumentation and the field of camera, and this is a relatively very fast evolving and new field. So what a wide field sky survey means is that um, instead of taking pictures of small parts of the sky, instead of doing that, what you do is you have an automated camera or an automated telescope which looks at the same part of the sky and scans the entire sky every few nights. And as you can see, for example, some of these telescopes like the ZTF or the Zwicky Transient Facility actually looks at area of the sky as big as 47 degrees. So for reference, that's a few tens of times more than what the moon appears on the sky. So I'll be talking mainly about this Zwicky Transient Facility, which is one of this wide field sky survey, which I currently work with. So what it does, it images the entire northern sky every 3 nights. As I said, it covers around 48 degree with its field of view. Every hour, it covers around 3,800 degrees, and it's around 200 times the size of the moon, just for reference. And it's currently mounted on this 48-inch telescope at the Palomar Observatory. So this is the Palomar Mountains that I talked about. So this is the famous 200-inch telescope, which was the largest telescope from 1930s to around 1960s, where people like Zwicky, Hubble, Chikra worked on. There are other telescopes like the Peak 60-inch telescope, and this is the 48-inch telescope where the Zwicky Transient Facility is. So there was in a recent big news from the Zwicky Transient Facility, they successfully classified over 10,000 supernovae. So as I mentioned, they were discovering just tens of supernovae just a few decades ago. Now we have reached the magical number of 10,000 supernova being successfully classified just from this one sky survey. So I'll move on now, connecting all of this to my research work. Hopefully, whatever I've explained so far has been clear. Please let me know if you have any questions, or if you have any questions, feel free to stop me at any time. So this is me at the 200-inch telescope. So my research work is primarily based on some of the optical telescopes at the Palomar Observatory. This is the 200-inch, the Zwicky Transient Facility being at the 48-inch telescope. And what I currently do is I'm currently leading this survey called ZTF, Census of the Local Universe Survey. So or I'll call it CLUE for the rest of the talk. So as the name census probably makes sense to you. For example, we have census of populations every 10 years in India. It's similar. We want to follow every transient, every supernova that exploded within a local volume of 150 megaparsecs. I don't know if megaparsec probably makes intuitive sense. So for example, the nearest galaxy, Andromeda galaxy, is roughly 0.8 or roughly 1 megaparsecs away. So this is actually a very large volume, has like it includes like millions of galaxies in this volume, but in the cosmological scale, we still call it a local volume. So the goal is to basically try to understand what each supernova that exploded within this local volume of 150 megaparsec actually is. To do that, what we do is that, as I mentioned, we need spectra, we need spectrographs to actually understand what elements are present in those. And only by understanding what elements are present in each of the supernova can we categorize them into different types. So if a supernova is very bright, so astronomers have this weird unit system called magnitude system. So if a supernova is very bright, the magnitude number is actually a bit lower. So if it's brighter than something called 18.5 meg, we use a 60-inch telescope on the Palomar Observatory, which I showed in a picture before. If it's a bit bigger, we currently use the 200-inch telescope, or we use the Keck telescopes, which are 10 meter in diameter. So these are one of the biggest optical telescopes in the world currently in Hawaii. So the way the entire system works, we have ZTF, which discovered a supernova. Then we know that, hey, we now have something that exploded in this part of the sky. Now we want to obtain a spectrum of that object so that we can diagnose what its nature is, right? So what do we do now that we have this big census? What science can we extract from this experiment? So there are primarily two types of science results which come out of such an experiment. One is that once we have been following hundreds of supernova over a period of 3 years, we often find some very rare gems, right? So some objects which just throw us off, like which doesn't match into any template that we already know of. It's some of these explosions are like very fast evolving. They're very bright, they're very faint, they show elements which should not be there. So there are all kinds of puzzles which come up in the study of a lot of these objects. So one is that you take this weird object and then you dig into it, follow it up with telescopes all around the world, do very detailed analysis of this one single object, and then put out your results about of your understanding of this one object. The other kind of analysis which can be now done, since this experiment is now a few years old, is that we now have this gold mine for statistical analysis. So as I mentioned, the field of transient optical astronomy is relatively new. So a lot of these rare objects only have few of its kinds in the literature. But with a big survey like this, now we have a statistically significant enough big sample to actually do some sample analysis on this various kinds of various flavors of supernova explosions. So to proceed onwards to my science motivation or the exact science that I'm interested in. So I'll start out with this very basic picture of basic concept that the way a star evolves or the way it explodes is all decided by the star's mass. So a star has different properties, right? It has different colors, it has different temperature, it has different radius. Sure, it has different chemical abundances. All of this do play a role, but if you had to pin one parameter that decides the fate of the evolution of one star, it is the stellar mass. How massive the star is kind of decides how it would evolve over time. So a low mass star has low mass, hence kind of like um, it's a very weird analogy that I have drawn between this is also seen in, for example, cars. For example, smaller cars have a smaller fuel tank, kind of similar to a small lower mass star, but they also burn through that fuel more efficiently. So they live for a longer time. Unlike some of the bigger cars, which have bigger fuel tanks, but they also burn through that fuel very rapidly. So they kind of die young. So the lifespan of bigger stars is actually smaller than lower mass stars. So what happens as a result of that is that in this entire life cycle of a star, where it evolves on to its various nuclear fusion stages, um, for example, if a star is less massive, what happens is that it becomes something called a red giant star, and then once it runs out of fuel, it would end its life as something called a planetary nebula, and then become a white dwarf. This is the fate of stars like our sun. So our sun will eventually undergo this fate after 5 billion years. But if a star is, say, 10 times more massive than the sun itself, then what happens to it is that it becomes something called a red supergiant, and then it's so massive that it undergoes this process called core collapse supernova, which I explained in the first few slides, and then leaves behind a compact object called a neutron star or a black hole. But where does this mass boundary exactly lie? What is the exact mass, or what mass decides whether the star should explode or whether it should not explode? Currently, based on theoretical prediction or something called a Chandrasekhar limit, the mass boundary is supposed to be around 7, 8, 9 solar masses, but this is not exactly known. So also, the number of stars. So the takeaway point from this is that if a star is more massive than around 7 or 8 solar mass, then the fate of that star would be that it would undergo a supernova explosion, the kind I have been talking about in this talk. As I mentioned earlier, so more massive stars end up dying more quickly. They are also less of those formed. So what happens when you take, say, for example, thousands of stars that you see in a particular galaxy, and if you plot them as a function of what its mass is, you'd see that a lot. Oops, there are a lot more low mass stars. For example, stars like our sun, there are a lot more of those compared to stars that are, say, 10 solar mass. There are a lot more 10 solar mass stars compared to, say, what a 30 solar mass compared to the number of 30 solar mass stars. So the stars that are basically in this mass boundary, say between 7 to 12 solar mass, actually should account for 40 to 50% of all massive stars that should explode, right? Just based on this. So you expect that the number of supernovae that we have observed, we should probably a few thousands of them should belong to this 8 to 12 solar mass range. But that's not what we observe. So in the last 40 years or so of supernovae observations, where we have seen like 5,000 plus core collapse supernovae, only 20 or so have been confirmed to belong to this low mass end of core collapse supernovae. And I won't go into the details of it, but a likely explanation is that compared to, say, a 20 solar mass which explodes, a low mass star has less mass, has less energy, has 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 less mass and less energy, so it explodes with lower luminosity. So basically, it would be fainter and harder to detect. So one reason why instead of say 2,000 such supernovae, we only have seen 20 of those is probably because they're just faint, and our current surveys, our current telescopes are not sensitive to those. So understanding this low mass end is very important for multiple reasons. For example, currently there's a mismatch between the number of supernovae that we see in the low mass end versus what you'd expect from just based on the counts of stars. This is very critical for understanding stellar evolution and late time mass loss that happens in these big stars, because this is where the switch between something called a red supergiant or between a red giant or something called a super asymptotic giant branch star. So it's very critical. This is the mass range where you have different things happening if you just change things by say zero point 0.1 solar mass. And this is very poorly understood theoretically because this is very hard to model for a number of reasons. I won't go into the further details of this, but one reason why currently it's a very exciting topic to study, this low mass end of core collapse supernovae, which is like 8 to 12 solar masses, is because very recently, we now have surveys like ZTF, which observes the sky repeatedly, almost on a 1 to 2 day cadence, and also goes very deep. By deep, I mean it observes very faint things. And also, very in the last 3 to 4 years, there have been a lot of recent progress and theory on this. People have started doing 3D simulations of the supernova explosions of this low mass end. They have started modeling this low mass end a bit more accurately. So it's a very exciting time to study this. Study more of this. So I'll just highlight two results from what we have done from the Census of the Local Universe experiment so far. So what we believe is the faint of single stars. So when I say single star, it's like sun, which does not have a companion. So if it's a binary star, then you have two stars orbiting around each other, or at least gravitationally influencing each other. But if it's a single star, then yeah, there's no other star within the gravitational bound of that particular star. So for those stars which effectively evolve as if it's a single star, the most likely fate of those are called something called red supergiants, which I showed in the cartoon earlier, and they are likely to explode as something called a low luminosity type 2p supernova. I won't go much into the jargons of this, but low luminosity, as I said, it's a low mass, so it's likely has a lower luminosity, lower energy. And what type 2 implies, it's that there's hydrogen present at the time of explosion. Remember, I showed the shell structure. So if the hydrogen shell is still intact at the time of explosion, when you point your spectrograph at it, you'll see lots of hydrogen there. And then we classify it as a type 2 supernova. So before this clue experiment started, so the rates of faint supernovae are not very well known. So here on the x-axis is how bright, how intrinsically bright that supernova is. And on the y-axis is their rate based on observed numbers. So as you can see, when a supernova is fainter than around -16 magnitude, the uncertainty in the rate is huge. The main reason for this is that the number of faint supernovae observed were very low, on the order of like single-digit numbers, because the surveys or the telescopes were not sensitive enough to discover a lot of these faint things. So one major result from the ZTF clue experiment, or the Census of the Local Universe experiment, is that now we have, because of around 40 to 50 supernovae that have been discovered, which are faint than -16 mag, we actually are able to put very, very strong constraints on how many supernovae are there on the faintest side of core collapse supernovae. And we, as I mentioned, we expect that 40 to 50% of all stars that explode should be in the 8 to 12 solar mass. And but based on the recent constraint that we put on the rate, we only see that it only accounts for 9% of all core collapse supernovae. So it's kind of a mystery, or kind of a mismatch between the expectation from the stellar evolution point of view and based on the number of exploding stars that have actually seen and have very strong constraints on right now. So this is the fate of single stars. But in the universe, most stars, especially if they're massive, are actually in binary or triple star systems. So instead of being single, there are two stars of different masses orbiting each other, interacting, and also. So in this plot, the x-axis is the mass of the star. So as you move to the right, the star becomes more massive, and on the y-axis is the multiplicity fraction. That is, how many of those stars have more than one companion, or have at least basically a binary or triple or higher. And as you can see, as you move up, for example, stars in the 8 to 12 solar mass range, which I'm interested in, almost 80% of those stars are actually in a binary star system. So that could be a reason. For example, in the previous analysis, I only tried to look for single star explosions, and maybe actually I should be looking for stars which are in binary systems. So um, not only a lot of those stars are in binary systems, but they also interact. What do I mean by interact? It's that the bigger companion, the more compact companion strips off stellar material from the bigger companion. So you will see that the outer envelope of the bigger companion, which was hydrogen or helium, actually is lost to this more compact companion. And then it explodes as something called a stripped envelope supernova. So as the name suggests, the outer envelope has been stripped at the time of explosion. Hence, it is called a stripped envelope supernova. So probably the next question is, can this kind of supernovae now account for this missing, this 9% versus 40% discrepancy that we have seen from our measurements so far? So once one so this kind of stars this kind of supernovae are even harder to discover because they are not only faint, they also evolve quickly. What it means is that they're only visible to the current telescopes on Earth for like a few days. If you miss them for a few days, then they just fade so fast that you can no longer observe them. So this is one category of supernovae which have been very, very poorly understood, mainly because of the limitations of the survey so far. So what would the explosions of this look like? So if you are in such a binary system, what your evolution would look like, it's a very complicated diagram, but what it would roughly look like is that you start out as a binary star. One of the bigger star basically loses its outer envelope to the other companion. Then you become something called a main star, helium star binary, because you've lost the outer hydrogen. And then one of the star now undergoes a supernova and leaves behind a neutron star, and then you become something called a high mass X-ray binary. I think this was the topic of one of the talks in this series. And then what happens later is that the remaining star also now loses its outer envelope. So basically what happens is this particular star has lost its outer envelopes multiple times because of this binary interaction. And as a result, at the end, what happens is that you are left with very little mass before exploding. And this is called something called strongly stripped or ultra stripped supernovae. And what it leaves behind is this double neutron star systems, which which are of interest for multiple reasons. And we believe we discovered another supernova belonging to this flavor from this Census of the Local Universe survey. Um, just to again highlight how unique this object was. As I mentioned, when your outer envelope has been stripped, you evolve very fast because you have very little mass left, and so you reach your peak brightness very quickly, and then you fade off your brightness very quickly as well. So this figure has all supernova detected in the literature from Zwicky Transient Facility, and on the x-axis is how quickly you evolve. So as you move to the right, the slower you evolve. And as you move on the y-axis, as you move up, you are brighter. So this 23 ZAW even occupies a very lonely corner in this phase space. So you can see that it's the fastest evolving faint stripped envelope supernova that we have discovered so far. It had the lowest radioactive material synthesized seen in any stripped envelope supernova seen so far. And it also highlights the fact that these objects are very hard to discover. So probably we need a lot more of this discoveries to actually constrain the rate of this faint of this low mass end of core collapse supernova, which is kind of a future direction that I'm looking into. So as I mentioned before, these are kind of objects which leave behind double neutron star systems. So I thought I'll add this animation because this is something when the two neutron stars are orbiting each other, you emit gravitational waves, which was the topic of the last talk. So I think it's cool when you connect various astrophysics topics and see how they're interrelated. And also for a fun fact, this process of two neutron star merging was first discovered in 2017 by and one of the groups which led the effort into the follow-up of this discovery was the same group I am currently working in, and they also saw signs of gold. So if you're a fan of gold, or if you've seen gold in your household and wondering where it first formed, it's the merger of these neutron stars which actually forms those gold atoms, which finally made its way into Earth, and now that we all love. Now, I mentioned that it's supposed, for example, the supernova that I mentioned, it's proposed, or its properties are indicative that it forms a double neutron star system, but we are not sure yet. So I thought I'll also add this because it shows how astronomy research in this particular field works. So you discover a particular supernova, you believe that the early properties of this are expected to be something, and then based on that, you make prediction for what it would be later. For example, if you form a two neutron star system when it's very young, it's supposed to emit the temperature of that system is supposed to be very high, and it's supposed to emit X-rays for after like around 300 days of explosion. And we have approved I have approved program from this Chandra X-ray telescope to actually observe this later this year. I'm excited. If we do detect, this would be the first detection. This would be the first time we see the birth of a neutron star system binary. This would be the first direct evidence for the birth of a double neutron star binary. And also this Chandra X-ray telescope, I think probably this was also talked about in a previous talk. I think it's really cool that this is named after S. Chandrasekhar, who had his roots in India, and did a lot of work to understand the supernova explosions and what the fate of stars as they die should be. I'll end with the future section. So as I mentioned, for example, stars like 23 Zov were very fast evolving and very faint, and they're very hard to classify. So we have only seen like 2 or 3 of them in our entire history of supernova observations. So one question that arises is that if you're supposed to be 40% of all stars that explode, then why are you so rare? And the most likely explanation is that it's an observational bias where our current technology, our current surveys do not allow us to like observe this supernova in this occupying this particular phase space. So I'm currently designing an experiment called the CATS 150 experiment. So it's called the Complete Astronomical Transient Survey within 150 megaparsec. This particular experiment starts on 1st February 2025. It's supposed to be a 6-month experiment with the Zwicky Transient Facility. And the main driving force behind this is this new instrument called the Next Generation Palomar Spectrograph. So I mentioned its spectrograph is kind of a fancy prism, which disperses light, and then you can classify what kind of explosion that particular supernova was. And as you can see, I won't go into the details, but the y-axis here is kind of like how efficient your spectrograph is. And the black line here is the efficiency of this new next generation Palomar spectrograph. It's competitive or better than any spectrograph around the world. And with this, we believe that we can now actually target the very faint supernovae and actually classify all of them with like a greater than 95% completeness, unlike in any previous survey so far. And I believe that once we actually do that, a lot of this missing supernovae in the faint and in the low mass end of core collapse supernova should actually show up now, or at least we will see based on what we see in the next 6 months. But yeah, I'm very excited about this starting next month. And this next generation Palomar spectrograph is a very new instrument. It was actually just installed a couple of months ago. I'm actually observing on Palomar with this particular instrument tomorrow night. And this is pictures from just last month when we were actively installing this new spectrograph on Palomar Observatory. So this is this 200-inch telescope, 200 inches, like 5 meter diameter telescope. The dome is really huge. And yeah, it was really nice to be part of the whole instrumentation project where you see how what goes behind the scene of a successful telescope, what goes behind the scene of a successful instrument, how do you make sure how do you make sure it works well, and what are the challenges that you need to overcome. So yeah, it's been a very cool experience, and it's also been very successful so far. So just on the second night of commissioning, so commissioning is basically nights when you're trying to make sure nothing's wrong with the instrument, you're trying to calibrate a new instrument. We actually classified a new supernovae on the second night of the commissioning itself. So as I say, classification is basically understanding which elements are present and what its physical origins possibly are. So we are all set to begin the SCATS experiment with this new spectrograph on the sky from 1st February this year. Yep. And moving out from Palomar, moving out from Caltech, the main thing I'm very excited about is this Vera Rubin Observatory. So it starts its operation in 2025 October, hopefully. So this is the telescope in Chile, and I told that ZTF has been very successful in going into observing thousands of supernovae every year and observing very faint supernovae. In terms of observing faint supernovae, this instrument is going to overshadow, or it's going to overshadow any survey telescope so far. For example, I mentioned today we discover around 10,000 supernovae every year, or a few tens of thousands of supernovae every year. Once we have this Rubin observatory on sky, we will be discovering on the order of 3 million, probably add an extra zero, we will be discovering around 3 million of supernovae every year. So you can imagine the huge number of objects that we'll have. It's a challenge, but at the same time, it's also exciting, especially because it's going to be very deep, which means that we will now actually discover a lot of this very faint transients of very faint supernovae, which has been a bit challenging to discover so far. Yeah, so this is also another area I'm very excited and looking forward to for later this year. So just to summarize the future of the entire field of supernovae or transient science, we do not just rely on optical telescopes. As I mentioned, for example, I have a proposal to follow up with X-ray for different programs. We have follow up with other wavelengths like radio, UV, for example. I think you have seen talks on like radio observations of astronomy and stuff. So to get the complete picture of a particular kind of astrophysical phenomena, you want to observe at all kinds of wavelengths. And the future is very, very exciting for the next decade. I think this is easily one of the fastest moving field currently in any, I would say, any subtopic of astrophysics or physics for that matter. So in X-ray, we have this new telescope called Einstein probe. We have this S-foam in ultraviolet. We have this telescope coming up called Ultraset. In optical, I showed this Rubin Observatory. We also have we have lots of exciting facilities in the millimeter wavelengths and the radio wavelengths, some of which also India is part of. So it's going to be a very, very exciting time. I think there will be lots of very juicy discoveries. We'll be understanding the physical phenomena behind a lot of this already existing transients, but the thing I'm most looking forward to is possibly discovering more of this rare gems, which we have never seen before. Okay, so I'd like to end with that for my science part. Okay, any questions?
Yeah, Kaustav, just a very basic question from my side. So what is the
Mhm.
difference in the spectroscopic signature that low mass supernovas and high mass star supernovas they leave? Like how do you
Yeah,
detect?
that is a very good question. So I didn't add the details for that, but the way to understand the mass of a star, I would say there are three different ways. One is that you look at the star itself, which exploded. For example, I now currently have images of, say, for example, a nearby galaxy and all the stars there. And then one of those stars exploded, then I go back and look at the image that existed of that particular star. And based on the color, temperature, based on how the star is supposed to evolve, I can predict what the mass of the progenitor star was. So that's one way, but that's a bit rare because your supernovae have to be very nearby for you to understand, for you to have those pre-supernova images. The second way is that you try to understand the light curve evolution. For example, how quickly did the luminosity change? How bright was the supernova light curve itself? So you do several. It's a very open field currently. I feel it's not very there's no clear answer to this, but you do various kind of radiation hydrodynamic simulations. You do various kind of pen and paper analytical expressions to try to understand this, but most of it is now moving to this numerical radiation hydrodynamic simulation. So you try to map your observed luminosities to progenitor properties. And the third way, which is the most probably robust way and that I utilize the most, is something that you wait for the star to faint, to become fainter. For example, when a supernova explodes, when you look at the spectrum, you're looking at the outer envelope. And the outer envelope is kind of doesn't tell you the story about the whole star. So you wait for around 200 days and then you take a spectrum. And now what happens is that the star is not transparent up to its very inner core. So now you start seeing elements like oxygen, like calcium, which are present at the core of the star. So just to give a simple relation, for example, the amount of oxygen that's synthesized in a particular star is very closely related to the mass of the star. So if we can detect oxygen at a very late time phase, say like after 150 days, then we can measure the amount of oxygen, and that oxygen we can map on to what the mass of the star is. So that's one of the main differences. Low mass ones have low oxygen, high mass supernovae have so high amounts of oxygen at like 100 days. Does that answer your question?
Yeah, it does. So when you're doing a population survey of, let's say, the different supernovae, so
Mhm.
which method do you, the last one probably? Like you look at the,
We yeah Yeah, when there's a big so currently the way I do it is, we do this follow up at late times, but this is a bit of an expensive process as well because when
yeah,
you wait
yeah,
for
yeah.
100 to 100 days, your supernova has become even faded out to become even fainter. And I'm already interested in things which are faint to start out with. But I've mainly used the Keck telescope in Hawaii, which is a 10-meter diameter telescope, which can actually observe very, very faint things. So I have a program to go after nearby supernova that are discovered as part of the census of the local universe, and we take this late time spectrum or we try to take as many as possible. And the other more general way to do it is through this light curve modeling, which is a easier, less expensive way. So we use all of them and then try to see if they're consistent.
We also have one question in the chat box. So probably I'll
Um,
read it out. So how powerful are these telescopes? Have they penetrated a few thousand galaxies to observe various supernovae, or is it limited to very few galaxies?
very good question. Um, So the power of this telescopes has well, by power I assume you mean how far we can observe, has changed over the history of time. So currently the Zwicky transient facility that we use can easily probe bright supernovae up to like around 500 megaparsecs or so, which is like if you assume a sphere of radius 500 megaparsec that has a few billions of galaxies inside. So yeah, we can look really, really far. And the Rubin Observatory, which I mentioned at the end, which would start operation this October, it can look up to cosmological distances. So I don't know if you're familiar with this term called redshift. So it can probe supernovae at redshifts at like one point something. So that would be looking at the volume that's like thousands of times more than the volume we are currently sensitive to. So we are improving that volume we can probe with every generation of telescope that comes. But yeah, the current ones also can access a lot.
So participants, if you have any more questions, you can directly unmute and ask.
I just at the career part of it. I just got the read your email to include that later. So I just included a very brief overview of my career, short career trajectory, and like one slide on if you have any questions on research careers. So so
Sure.
as it was already mentioned, so I did my bachelor's in physics from IIT Kanpur till 2020. I had a couple of research internships, one at TIFR Pune in 2018. I had a summer research intern at Harvard in 2019. And then I moved on to do my master's in astrophysics and PhD from 2020 onwards. So I do not have a time to I did not have the time to like add a lot of details about the application processes and all, but this is something which is very close to my heart. I thought when I was in my undergrad, even though I was from a pretty good college, there was still lack of resources about how to apply, what to apply, unlike say the industry jobs where they had lots of workshops and training on all these application processes. So right when I finished my bachelor's, I did the series of interviews with people, with friends at some studying at many of the top colleges all around the world. So I think there are lots of talented people who just do not know what to do or how to move forward. So I think this is a series of interviews. If you go on YouTube and search Kaustav Astro, there's the series of talks which would cover almost all queries about how to go about applying after you're done with your bachelor's. And also in all of this, I guess most of the people who would be listening to this are bachelor students. So they also talk about what to do during your undergraduate time, how to make sure you are approaching the correct direction if you are interested in a career of research, or how do you even find out if you should do research versus say applied industry jobs and all. So I definitely recommend this if you're interested to start out with. I also made a recent talk in SMEs for um, Kamrup Rural District Commissioning Government. So it's in SMEs. It's in the same YouTube channel, so you can also start out with that. And you can also contact me on any of these platforms. I'm more than happy to usually answer your questions.
Yeah, great, great. So we have another question in the chat box. It's from Kasturi. So if two supernovae occur very close, does it merge, or maybe the remnants, do they merge? And if they do, like how can you distinguish between the two spectrums?
Oh, yeah, another excellent question. So this is actually a problem now, but well, I'll start out with the basics. So I would say the universe is actually a very, very empty. Uh, it's actually very empty. For example, our nearest neighbor, our nearest star next to us is like 4 parsecs away. So even if you take a look at the picture of any nearby galaxy, stars are kind of there's an offset between different stars by like a few arc seconds or so. Again, arc second is basically a unit of angular separation. So it's very rare that two supernova would occur within, say, the angular separation which a modern day telescope can resolve. So I would say a logical follow-up of this is that, for example, if I'm using a telescope with lower resolving power, when I observe two supernovae, it could be that maybe they are very close to each other. But if I then do follow up with a high resolving power instrument or telescope, then I can actually look with this higher angular resolution. I can actually see if they're actually further away or not. And if they're actually further away, then we need to obtain spectrum. When we obtain the spectrum, they will have signatures of both the supernova. So it'll be very hard to disentangle unless you can actually resolve the angular separation between those. And we have often seen this. It's now called a sibling supernova pair. So I think Zwicky Transition Facility has started because we are observing tens of thousands of supernovae. All kinds of very rare things also now are becoming, they are getting discovered. So these are called sibling supernovae. And we are still able to resolve them, but they are a bit of a struggle in terms of separating the different spectrum. But if you talked about remnants, I guess the supernova remnants can actually only be supernova remnant is basically the fancy structure of the supernova that I showed, which is left after like thousands of years after a supernova explodes, and we can only observe them in our own galaxy. And usually, yeah, that's a very different science from what I talked about today. When we obtain a spectrum, we are looking at the point source on the sky, not an extended region. So as long as you can tell 2 points apart, you're good.
Yeah, so any more questions from the participants? Or maybe not something related to the talk, like even any such questions. If you have, you can type in the chat box. Anyway,
Yeah, feel
I
free
have
to ask
one.
anything. Yeah.
Yeah, yeah. So, like, in addition to the mechanism that you proposed, which is the USSL, so do they have any other mechanisms proposed for the discrepancy, like the 40% and the 9% observed discrepancy? So, what other
No,
mechanisms do they? Huh.
yeah, this is, as I said, this is a bit of a more recent field. So only
Hmm.
recently have we started actually probing this very faint supernovae. A few ways in which it can be explained. One, I think that one likely explanation is that when you explode, you have a lot of dust around your star. So what happens is that whenever there's a lot of dust, the optical brightness reduces, and that's reprocessed into the infrared. So, for example, it's like when we look at the sun and there's a lot of atmosphere between us, the sun appears redder because of the same reason. So that could happen is that a lot of this low mass N stars, when they explode, they have a lot of dust around them. And then so they're already faint, and this dust also makes them even more fainter. So that's one reason that they're very dust obscured. And the way to solve this mystery would then be to look at the infrared telescope surveys. And they're also actually a very new field of study. There's some progress into infrared time domain surveys. Actually, our group itself, a lot of people are interested in this, trying to discover transients which are missed in optical wavelength but can be seen in infrared because they're so dusty. So that's one explanation which comes to my mind right now.
So, can we use the already existing infrared telescopes, or we have to build something else for the sky surveys in the infrared?
Yeah, so currently there are no very sensitive infrared telescopes. The main reason for that is that infrared detectors are very expensive. So, for
Yeah.
example, the ZTF camera is a few megapixel, but the infrared detectors, the conventional infrared detectors, are around 10 times costlier than the optical CCDs. So, to get the same resolution, so if you have the same fund, the resolution that you have is 10 times lower, which makes things very hard. So it's a very new field of technology that's emerging. So there's this new thing called gallium in gas detectors, which is a very new technology which is being used by our group to actually build a new survey that's currently not started yet, but would start soon. So more surveys like that are in the queue. The other way to do is, of course, go to space, where you have absolutely no atmospheric problem, no
Yeah.
problem. Yeah, but again, there is this telescope called the Spitzer telescope, Spitzer Science Telescope, which operated for around a decade. But they're also, yeah, but it had a very narrow field of view, so it was not good for, say, observing the entire sky. But actually, it did have a very wide field of view, but it could only detect, like, it could not go very deep. It could not discover very faint things.
Mhm.
Yeah. Any other questions on the science, or just any general astronomy question, or any research or career related questions?
So, if no questions, maybe Costa, we can conclude this session. And for
Yeah, sure.
the participants, you can always contact Costa through these channels that are popping up on your screen. So yeah, so Costa, yeah, thank you for giving us your time for this session. and
Yeah,
best wishes for all the upcoming projects that you are working on. So
yeah, thank you so much. And also congratulations to you for organizing this great series of talks. I think I also found that very helpful. It's really nice that someone's doing this for, I think, students from Assam. It's really
yeah.
commendable.
Thanks a lot. So I hope. So any final remarks from your side before we end this session?
Yeah, for those, if someone's watching on YouTube or later, as I mentioned, feel free to contact me on any of the given platforms. And if you have any science or career related questions, I'd be just let me know that you found this links through this talk. Then I'd probably like prioritize that. And yeah, I'm happy to answer any such questions. Yeah. And good luck to everyone who's listening to this.
Yeah. So thank you, Kaustav, and do let us know if you visit home. So maybe we can plan
Yeah.
something offline also.
Okay. Yeah.
Yeah, very great. Yeah. So yeah,
Bye.
thank you. Bye.